Welcome to the Explainer. Today, we're basically going to be architects. We're building a database from the ground up, and that means getting to grips with its core design principles. All right, so here's the game plan. Think of this as our construction roadmap. We'll start with the blueprint, talk about the fundamental laws of data, kind of like the laws of physics for our structure. Then get into the building codes, how to remodel without knocking the whole thing down, and finally, we'll look at the absolute strictest standards for a perfect finish. Okay, first things first. Every single great building starts with a plan, right? Well, in the database world, that plan is called a schema. This is the absolute foundation for everything else we're going to build.
So what is a schema, really? It's the blueprint. It's the architect's drawing for our database. It lays out exactly where everything goes, the tables, the columns, the relationships, long before a single piece of data is ever stored. It's all about the logical structure, not the physical bits and bytes on a hard drive.
Now, diving into that blueprint, you'll see that not all rooms are created equal. It's a really important distinction. You've got your strong entities. Think of something like an employee record. It can stand on its own because it has its own unique ID, its primary key. But then you've got weak entities, like, say, an employee's dependent. They can't be uniquely identified on their own. They absolutely depend on that owner entity to even exist in the database. Yeah, take that dependent example. The only reason a dependent's info is in the company database is because the employee is there. If the employee leaves the company, poof, the dependent's data is gone too. This is what we call total participation. A dependent just can't exist without being tied to an employee. And you'll see in diagrams we use special symbols, like that double rectangle, to flag this special dependent relationship right on our blueprint. Okay, so we've got our blueprint. We know what our rooms or entities look like. But now we need to figure out the rules, the laws of physics that control how all the data inside those rooms relates to each other. These rules are what keep our data logical and consistent. And the big one here is called a functional dependency, or FD. It's just a fancy way of saying there's a relationship where one piece of information reliably points to another. When you see that notation, X with an arrow to Y, it just means X determines Y. If you know X, you should be able to find one and only one value for Y. It's like a cause and effect rule for all your data.
And this table, it's a perfect illustration of what happens when that rule gets broken. So if our rule is student ID determines student name, look at that third row. It's a complete no-go. A single student ID, number one, can't point to two different names, Ranjit and Varun. That's an invalid state, and it's exactly the kind of thing that messes up a database, creating total chaos and ambiguity.
So how do we stop these kinds of structural nightmares from happening? Well, just like in construction, we have a set of building codes. In the database world, we call them normal forms. They're basically a series of guidelines that help us get rid of redundant data and really lock down data integrity. The first and most basic building code is called first normal form, or 1NF. It tackles a super common and messy problem, trying to cram way too much information into a single field. The rule is dead simple. Every single cell in your table has to hold one and only one indivisible piece of information. Just look at this. You see how for the student Psi, the course column has C, C++? That's a classic multi-valued attribute. It completely violates our first building code, and honestly, it just creates a mess. Imagine trying to find all the students who are taking only C++. How would you even do that? It's clunky and super inefficient. But you know what? The fix is actually really simple, and it's super powerful. We just break the table up a bit. We decompose it. So now, each cell has just one atomic value. You have one row that says Psi is taking C, and another that says Psi is taking C++. See? The data is clean, it's clear, and most importantly, it's following the rules. All right, moving on up. Our next building code, third normal form, deals with something a little more sneaky. It's called a transitive dependency. This is what happens when an attribute that isn't a key, we call it a non-prime attribute, depends on another non-prime attribute. So in this example, the city depends on the state, but the state depends on the roll number. That means roll number indirectly decides the city. We really want to get rid of these chain reaction dependencies because they cause all sorts of problems when you try to update, add, or delete stuff. So here's the bottom line.
When our design breaks these building codes, the fix is usually to remodel. We have to split a big, clunky table into smaller, cleaner ones. But, and this is a big but, how do we do that without wrecking the place? How do we make sure we don't lose information or, even worse, invent data that was never there?
And that leads us right to this critical question. When we split up a table, how can we be absolutely sure that we can put it back together perfectly? We need to be able to reconstruct the original data without creating any of these, phantom records.
Turns out there are two golden rules for doing this kind of remodel right. They are absolutely non-negotiable. First, the lossless join. This means when you join your new tables back together, you get the exact same data you started with. No extra junk, no missing pieces. And second, dependency preservation. All those original laws of physics, our functional dependencies, they all still have to work and be enforceable in the new setup. So what's the secret sauce for that lossless join? Well, it's all about the connecting piece. The attribute that the two new tables have in common must be a key, a candidate key or a super key in at least one of those tables. This common field acts like a solid anchor, letting us piece everything back together perfectly without accidentally creating those phantom records, which are basically just made up, incorrect data. All right, time for the final polish. We've talked about the standard building codes, 1NF, 3NF, but for the true perfectionists, there are even stricter standards out there to get your database design absolutely pristine. And that brings us to Boyce Codd Normal Form, or BCNF for short. Think of it as a premium-grade building code. It's a much stricter version of 3NF, and its rule is simple but tough. For every single functional dependency you have, the thing on the left side of the arrow, the determinant, must be a superkey. No exceptions. But, and this is a big one, there's a crucial trade-off. While 3NF always makes sure you can preserve your dependencies, BCNF, well, it doesn't. Sometimes when you're remodeling your tables to meet this super strict BCNF code, you might accidentally break one of your original data rules because it gets split across tables in a weird way and you can't check it easily anymore. And last but not least, to really streamline our design, we can create what's called a minimal cover. You can think of it as simplifying that architect's blueprint down to its absolute, most essential, rock-bottom set of rules. It's a three-step process. First, you make sure every rule has only one thing on the right side. Second, you ditch any redundant rules, ones you can figure out from the others anyway. And third, you trim any fat from the left side of your rules. What you're left with is the core, irreducible set of dependencies, which is so much easier to work with. And all of this leaves us with a final, really interesting question that every single database designer has to wrestle with. What's better? A database that's structured perfectly, even if it means you can't enforce a key business rule, or one that preserves every single rule, even if it has a few subtle structural flaws? It's that classic trade-off between absolute perfection and everyday practicality. Thanks for joining me on this explainer.